Nature is crazy. Although it looks kinda weird. Something doesn't seem right. There you go. Sun is also flat. But actually, the Sun is even less elliptical than the Earth, and it's much closer to a perfect sphere. There is no such thing as a flat star. Yeah? And what is this? But in all seriousness, some of you might think, what flat star is he talking about? Of course, we aren't going to talk about conspiracy theories, but rather about very much real objects, such as a very unusual star, Achernar. Our own planet is a bit flattened. The difference between polar and equatorial radius is about 20 kilometers. Gas giants are even more oblate. Jupiter's polar radius is over 4,500 kilometers shorter than equatorial. And for Saturn, this difference is even bigger, being 6,000 kilometers. But obviously it's not the proper way to compare how oblate different bodies are. After all, they are quite different in size. That's why astronomers use ellipticity to compare flattening of bodies. We can calculate it like this, and if we use Jupiter's polar and equatorial radii, we will get ellipticity. For the Earth it's about 0.003, for Saturn it is almost 1/10, and I'm not even mentioning Haumea, but Sun's ellipticity is this. The difference between polar and equatorial radii is only 5 kilometers. The Sun is the closest to a perfect sphere in our solar system. Well, and Achernar is the star as well, but it looks different. It's the brightest star in the southern constellation of Eridanus. It's a B-type hot blue star with a mass of 6.7 solar masses, and it is far from being a perfect sphere. It's a part of a binary system with a less massive companion. It's the 9th brightest star in the night sky, and the distance to Achernar is about 140 light-years from Earth. This is obviously not a photo, but that's what it might look like. Its polar radius might be 50% shorter than the equatorial radius, so it's one of the flattest, if not the flattest known star. And that looks weird, considering that this is what we usually picture when we think of a star. Perhaps many of you already have an idea of what might be a reason for such an unusual shape. A dwarf planet Haumea, for instance, has enough mass to be quite spherical, but that's what it looks like because of rapid rotation. But there's more to it than just an unusual shape. How do you even know it's flattened? First, we're very limited by angular resolution of an optical system. It's basically the smallest angle at which an optical instrument would see two separate objects as separate objects. Here, when two poles are close enough to the observer, we can see both of them. But should they get far enough, they would appear as a single object because of low angular resolution of our eyes. The higher angular resolution, the more detail we are able to see, and to increase angular resolution we need a bigger aperture. For a single telescope, that basically means a bigger mirror. This is how our eyes would see the moon, but with a telescope there is much more detail. We can observe some binaries as single objects, but at certain angular resolution we would be able to distinguish individual companions. This also applies to shapes of objects. So there is point light sources and extended sources. Observing the sky with the naked eye, people often confuse, let's say, Jupiter with just a bright star. But look at it even through an amateur telescope and you will see something like this. A telescope resolves the planet not as a single point, but rather as a disk, and it becomes an extended source. If we use an amateur telescope, any star is going to be a point source. That's actually an approximation, but that's fine for now. The thing is that we won't be able to see a star as a disk. Angular resolution of a small telescope is just not enough even for closest stars, and that is mostly true even for large scientific instruments. Even though stars aren't represented by just single pixels in images like this one, and they appear to be different sizes, that's basically not their actual sizes, but only a manifestation of brightness, so here their surface is not resolved. Now, only several stars have been resolved. Most famous examples are a radio image of Betelgeuse and an image of Antares created via infrared interferometry. Obviously, I never use Wikipedia as a source of information. This time it's the only place where I found a list of resolved stars. This list is incomplete, but it's at least something. It allows us to see that resolved stars are either supergiants or stars that are quite close to the Earth. And also, most of the images are created with interferometers and not single telescopes. Yes, we can resolve a galaxy a billion light-years away with the Hubble Space Telescope, which in modern standards has a relatively small 2.4-meter mirror. But it's hard to comprehend how much smaller stars are compared to galaxies. In theory, we can keep increasing the size of telescope mirrors, but sooner rather than later, there will be technological limitations. But there is another way to increase resolution. To use interferometers, systems of telescopes connected in a single network. If we place two telescopes, let's say 100 meters apart, and connect them, we would have an interferometer with a baseline of 100 meters, which would work as a virtual telescope with angular resolution equivalent to a 100-meter telescope. Of course, it's not as simple as it might sound. We have to synchronize them very precisely and do a lot of other stuff. Another disadvantage is that we don't have a collecting surface of a 100-meter telescope. Only angular resolution increases, but the amount of data collected by two telescopes remains the same. It can be, at least to a certain extent, compensated by the Earth's rotation. For instance, this technique was used to fill more area of a virtual Earth-sized telescope to create the first image of a black hole. And now let's get back to Achernar. We do have some resolved direct images of flattened stars, but in this case it's a bit more complicated. I've already said that the reason for this shape is fast rotation. Linear velocity of the Sun at the equator is 2 km per second. And now compare it to Achernar's 250 km per second. Sun completes one revolution at the equator in 25 days, and Achernar only in 2 days. But how can we know how fast a star spins if it's only a point source? We use Doppler effect. Spectral lines shift to the red part of the spectrum if the object is moving away, and to the blue part if it's moving towards us. This allows us to learn a lot about the object, from its angular velocity to its mass, for instance in binaries. And if we are looking at a star not directly at its pole, a part of it is receding and a part of it is moving towards us. If we observed a receding part separately, a certain spectral line would move to the red part, and the same line of the approaching part would move to the blue part. But again, we see it as a point source, so we observe the signal from different regions of the star at the same time. So those two effects overlap, and the spectral line that we actually observe becomes broader. And the broadening effect depends on the rotational velocity. Using this effect, scientists can calculate how fast the star rotates. Just the fact that we know how fast a certain star spins can tell us that it can be flattened. In the case of Achernar, there's also VLTI measurements of the angular size. The system actually consists of several large telescopes, but in the case of Achernar measurements, pairs of test 40 cm telescopes were used. The advantage is that it's possible to move them around in different configurations. Two separate baselines were used, 140 meters and 66 meters. Achernar was observed at regular time intervals. The Earth's rotation allowed to measure the angular size of the star from slightly different directions. This is a projection of the observations onto the sky. Here we're seeing pairs of points. Based on these multiple observations, the profile of the star was reconstructed and it turned out to be flattened. Actually, this axis is the largest possible extension, but the star is probably inclined to the observer, so it actually can be even flatter. Astronomers believe that Achernar spins close to the critical breakup velocity, and the unusual shape is not the only consequence of rapid rotation. There's some other interesting effects. Perhaps it is surrounded by the equatorial disk. There is some infrared observations that support that, as well as modeling. Also, there is probably the effect of gravity darkening. A rapid rotator of such a shape should have different surface gravity at poles and at the equator. Polar regions have higher effective temperature and brightness, and the equator in turn is darker and colder. The faster a body rotates, the stronger the effect. This image shows what it might look like. Achernar's polar regions are twice as hot as the equator, with 20,000 Kelvin surface temperature compared to 10,000 Kelvin. We haven't yet seen resolved images of Achernar, but you might have noticed that among resolved stars in the list, there were some other oblate ones. They were observed by CHARA, an interferometer that consists of 6 1-meter telescopes. and it has baselines up to 331 meters. These are several CHARA images, the stars that you have seen even with the naked eye. Some might say, wait a minute, if Achernar revolves once every 2 days and has such a shape, what about millisecond pulsars that spin up to several hundred times a second? Why in all of the images they are always shown to be perfectly spherical? But the conditions are completely different. Achernar's mean density is many times lower than that of water, whereas neutron stars are among the densest objects in the universe. Also, immensely strong magnetic fields resist flattening. As a result, it's quite the opposite. The surface of a neutron star is the closest to a perfect sphere in the universe, and yet even they aren't perfect. Also, I'd like to say that such unusual properties of bodies, interesting effects, methods used to study objects that far away, all of this is another proof for me that science is way more interesting than any conspiracy theory. Links to all of the information sources are down below in the description, and if you enjoyed the video, leave a like, comment and subscribe. Bye!